Excuse me, Dr. Tran.
Mhm.
Regarding the final project for 541, was there any report template that you wanted me to just put it there? Because I'm just writing on it like a simple Word and using the
Oh,
rubric.
yeah, I think I do have a template. Yeah, I'll send it to you after the class.
Okay.
Yeah,
I'll
it's
just-
it's mostly, I mean, the only thing I really care about is just that it's separated into sections. And so whatever font and stuff, I don't really care about that, but I just want it organized in sections just to make
I
it easier
think
to
the
read.
one that I saw from Rubik, it was like a methodology.
Yes,
And then an
yes.
introduction. That's it, right?
Yeah, it's the same sections as the rubric, but I lay it out in a template, but I
Okay,
can,
if you send me, that's great.
okay, yeah, I'll send you after class. Yeah. Actually, probably right now, we have some time right now, because I should still have it here. I know.
Did you open that file? What's that you do?
No, I haven't. I'm opening it.
I'm curious. I haven't seen it before, so I'm curious what it looks like.
How did you guys work on that at the same time?
We didn't. I fixed her mistakes, took screenshots, and said, "Do it this way." And so I think she just copied it. I'm not sure. That's why I'm really curious to actually see what it looks like right now. Professor, are you sticking around after class today? for a
Yeah.
little bit?
Yeah,
Okay.
I can stick around.
I desperately need help on the final project.
Okay. Yeah, that's what I stick around for, to answer questions like that.
I've been trying for like 2 weeks to stick around and talk to you.
Uh-huh.
But every time class ends, I'm like, oh, let's go.
Uh-huh.
Let's go do something else.
Oh, I see. I see.
I forget every time.
I just remembered it on SolidWorks.
Okay, I'll open it up right now.
That last one with Ansys Mechanical.
Yeah. Missing a server. I just mine for sure. Server packets never show up, but they're there. Let me give you. I'll send you mine. That's all. I'm looking at an assembly somewhere. It's a typer tool. A typer tool. There's 2 brackets, and it's connected by just 1 bracket. So any force on it's going to break it. So I'm preparing. So I just know what she said.
All right, it's 5:30, so let's go and get started today. All right, good evening, everyone. We have a riveting audience today, both on Zoom and in person. It's but I know people are busy, so I know how it is. But welcome. This is our last Ansys activity of the year. So how's everyone feeling today? Tired, yeah, I know we're all tired, but glad you guys can make it. I say this a lot, but I really do appreciate you guys coming out to the lectures. I know the lectures are recorded, and I do that just because I know you guys are busy, but it really means a lot that when the lectures are recorded that you guys still come and see me. So I really appreciate that. Okay, and so the plan for today is we're just going to be working on our activity. Okay, so this is the last one of the year. And the due date for this activity is going to be next Sunday, December 12th. Okay, so that's going to be the Sunday right before finals week starts. Okay. I don't think this is that time consuming an activity. It's definitely less time consuming than activity 5 because the jobs for this one are much faster than a dynamic simulation. So and so I've given this to my grad students and no one has complained. And so I'm not sure if they're just too tired to complain or if it's really not that bad. So hopefully it's the latter one, that it's actually not that bad. Okay, because I know we're all kind of busy this time, but it's an exciting one. Okay, and I picked this one to be the final activity just because I know this is something that a lot of you are interested in doing, especially those of you who are working on projects where you're doing kind of structural design of some kind of vehicle, right? So I know we have Formula, I know we have Baja, and we have Rover. This is going to be very relevant for you guys, and for senior design project as well. This is a great one because it's we're going to be learning how to find the natural frequencies in structures. Okay, and Ansys has a very nice tool for this called modal analysis. Okay, and with it we'll be able to very quickly find the natural frequencies. Okay, we'll pick up a couple other really nice small tools along the way too. So things like bearing loads, we'll learn as well. So I think that'll be a nice bonus. Okay. All right, and so I think that's all my announcements. And so the only other things that are out there right now is I think the dynamics activity that was due last night, or was it due this Friday? Last night. Okay. So I need to grade that, and then the final project member is due on December 20th, and so that's the Monday after finals week. Okay. All right, and so are there any questions I can answer before we get started? All right, okay, so let's go ahead and get rolling. So the files that you need for the activity today are on the Canvas site. And so if you go to our Canvas site and you go to assignments, you'll find Ansys Activity 6, Modal Analysis and Vibrations. And you can download the CAD file for this activity, as well as the PDF instructions, okay? And so as usual, the PDF has everything that you need to know about the activity. And then we're basically just gonna go through that today in class, okay? All right, so let's go ahead and open up Workbench, okay? And assuming that you downloaded the file, okay? And so where we're going to start today, even though the subject for today's activity is modal analysis, we're actually going to start with static structural, okay? I will say that if you're purely just interested in the natural frequencies, then you don't have to do a static structural first. So this is kind of an optional one. But I did want to show you what options are available to you if you do start with static structural. Okay, so we're going to start with that today. So let's go ahead and drag static structural over here. Let's go ahead and add in our geometry. And so we'll import the geometry and then we'll load in the gearbox. Okay. Oh, the subject for the activity today is a gearbox CAD. I haven't introduced that yet. Okay. And so this is a gearbox that you would find inside an engine most typically. And then inside this gearbox is a system of gears that's might be used for like a transmission system. Okay, and so I picked this one mostly just because this is a CAD that was provided by the textbook, which is nice. So I didn't have to make it. But also, whenever you have any kind of rotating parts, rotating mechanical parts like gears or something like that, then resonance and vibration should always be a concern because those gears are going to be turning at a fixed frequency. And that's going to put some vibrational load on your structure. Okay, and so you want to make sure that your structure is not going to resonate together with those, with those spinning parts. Okay. All right, so let's go ahead and open up Ansys. Go ahead and load in the gearbox geometry. Before we jump into mechanical, we have to load in some material data. Okay. And so let's go ahead and click on engineering data. And this will bring up our engineering data toolbox. Right? And so you can see here by default, we have just structural steel. And so for this activity, we need to add a couple more material properties. Okay. And so we're going to add them directly from the pre-made library. So go ahead and click on engineering data sources right here. Okay. We're going to go to general materials. Okay. And then from here, we're gonna load in two materials. And so the first one we're going to load in is stainless steel. Okay. And so for me, it's entry number 12 right here. So let's go ahead and click on this plus arrow or plus button right here. Okay. So that adds stainless steel. And the other one we're going to add is gray cast iron, which is number 8 right here. Okay. All right. And so the nice thing about using these pre-made materials, remember, is that all of the properties are already loaded. So you just have to click on the plus arrow to add it to your project. And so if you click on engineering data sources again, you'll see that we'll have 3 materials now. So we have gray cast iron, stainless steel, and then the default structural steel. Okay. All right. So is everyone able to load in the 3 materials? Yeah, question?
Yeah, I found it.
Oh yeah, it's a fairly long list. So yeah, just go to general materials here, and then yeah, just find gray cast iron and stainless steel. Yeah, stainless steel is a little bit different than structural steel. Yeah, that's why we're going to use it for this one. Okay. Okay, all right, and so if everyone's loaded the materials, let's come back to the workbench, and then let's go ahead and double click on Model. And so this is going to bring up Ansys Mechanical, where you know, we can perform the rest of the analysis. And so, you know, I will preface this by saying that, you know, I did this activity with my grad students before the break, and this computer specifically that I'm working on at the lectern here has a bug in the software, and so I won't be able to show you one aspect of the modal analysis, but I'll just explain in words to what you should see. And it seemed like all the other computers that feature did work. It's just for some reason this one is bugged, and I'm not sure why. Okay. And so we loaded in our gearbox here. Okay, so you can see it's a very simple representation of a gearbox. Right. First thing you should notice is that if you go to the geometry here, you can see that we have 3 different parts. And so we have the housing, we have the flange, and we have the base right here. Okay. But what you'll notice is that the housing has a question mark next to it, right? And so remember, question marks always tell us that, you know, there's something that Ansys wants us to set, you know, before we can move forward. Okay. And if you click on the housing here, you can see that there is a entry here, which is highlighted in yellow, which is the thickness of the housing. Okay. And so you're probably wondering, you know, why do we need to set the thickness for this guy, right? Well, let me go ahead and hide the base right here, and I can show you why. Okay. And so if you hide the base, silly me, I got the keyboard down here. Okay. And so if you hide the base, you can see that the housing here is a shell, is actually a shell model, right? And so it's you can see that it's been made really, really thin. Okay. And so it's effectively like a 2D surface. Okay. And if you recall from activity 4, whenever we have a shell model like this, we have to assign a thickness to it, right? Because that thickness is going to be what Ansys is going to assume when it does its calculations. Okay. And so for this particular model, and you're going to need to change the units for this. Let me go ahead and eliminate the annotations here. Okay. And so for this particular model, we're going to change the units to millimeters. Okay. And the thickness we're going to set is 3 millimeters, right? Okay. So go ahead and specify the thickness of 3 for the housing. Okay. If you fit in the base, you can show it again. Okay. And then that will be. All right. Oh, material. So we also need to set specify materials for these. Okay. And so the ones we're gonna select for the housing, we're gonna choose this to be stainless steel. Right. And so after you click on housing, go to the material assignment down here. Okay, and then change it to stainless steel. Okay, don't get confused with structural steel. And then for the flange and the base, we're going to assume that these guys are gray cast iron. Okay. All right, so just to summarize, the housing is stainless steel, right? And then both the flange and the base are gray cast iron. So make sure you specify those before moving forward. Okay. All right, any questions on this? Okay. Yeah.
Yeah, just, sorry, Kevin. So we're doing a static structural with cast iron steel and stainless steel.
Yeah.
And then we're switching the thickness to 3 millimeters per house.
Exactly. Yeah. 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 So if you're just, I noticed a couple people joined the Zoom call too. So if you're just joining, go to the Canvas site and go to Ansys Activity 6. You can download the PDF instructions here. So we didn't make it that far yet. And make sure you download the CAD model and load it into Ansys Workbench. Okay. Okay. All right. And so now that we've done with that, okay, the next thing that we have to check here is actually our connections. Okay. And so we have 3 different parts. And so we want to make sure that they're connected well. Okay. And so let's go to connections and then we'll go to contacts. Okay. And you can see here that we have one contact region already. Okay. And so the contact region here is between the flange and the housing. Okay. And you can see here from the bottom that this is a bonded support. But we don't have a contact in between the housing and the base, right? Which is bad because we want to make sure that our housing here stays attached to our base. So right now there is no connection. Yeah.
Is it just not connected right now because it was a shell originally?
Exactly, right. Yeah, and so this is exactly the case for activity 4. So if you remember for activity 4, we had to make all the connections manually too, and that's because we have a connection between a shell and a surface. Okay. And more specifically, if you want to be more specific, it's because the edge of the shell is what's being connected to the base, and so the edge of a shell is only just a line or an edge, and so Ansys is not going to automatically generate connections between edges and surfaces. Okay. And so we're going to need to add this manually. So let's go ahead and right click on contacts. Okay. And so let's go ahead and insert a manual connection region. Okay. Right. And then so we're going to select the bottom edge of the housing and the top of the base. Okay. All right. And so we need to specify these as the contact and the target. Right. Have we talked about in this class how to specify contacts and targets before? I know I've probably talked to a couple of you individually, but I don't think we've talked about it as a class before. So let me give you the kind of the logic behind it, because in theory, especially because we're setting these as bonded, I think it raises the question of which one should you set as the target and which one should you set as the contact, and the choice actually matters a lot. Because so let me do it the wrong way first, and then I can show you. Okay. So this is the wrong way, so don't copy this. Okay. You're going to need to do control click to get all the edges. Okay. And so basically we want to form a bonded contact between the top part of the base and the 4 edges of the housing that make contact with it, right? But you can see when I do it like this, then Ansys is not happy with it, and so it still has a question mark right here. Okay. And so the reason for that is because it doesn't like the order on which I've selected the contact and the target. Okay. And so, so in order to avoid these errors, you need to choose the appropriate parts as the target and the contact. And the logic behind that is for the target surface, which is the bottom one here, this one should be chosen to be whatever surface is either larger or is more rigid than the other one. Okay. And so for this case where we have a connection between 4 edges and a whole surface, the one that's bigger here is the surface, right? And so we want to set the target to be that larger face right there, okay? And the contact is the other one. And so, if you made a mistake like this and you set them incorrectly, you can go ahead and right click this, and there's a button here called flip contact and target, okay? And then once you do that, then Ansys will be happy, okay? And so remember, the one that's key here is the target. And so whatever you choose to be the target, that one has to be the one that's either bigger, or in other words, has greater surface area or greater volume, or it's the one that's more rigid. Okay. And so that could be, either the one where you apply a part where you apply a fixed support, or it has a stiffer material and things like that. Okay.
Where's
But-
that flip button?
Oh, so if you want to flip it so you right click on the contact and you click on flip contact target. Yeah. Mhm. Yeah. So so I mean, so you don't have to flip it. And so I only flipped it because I did it incorrectly at first. But if you want to do it correctly from the beginning, you would select the top face of the base as the target, and then the contact will be the 4 edges at the bottom of the housing. So actually, let me do it from scratch again, and I'll do it correctly this time, so I don't have to flip it. Okay. All right, so go ahead and insert manual contact region. Okay. And then for the target, I'm going to go ahead and select this face. Okay. And then for the contact, which is the smaller of the two, I'm going to select the 4 edges around here. And you're going to need to do hold control and click in order to select all 4 edges. Right, so just like we did with the car crash. Okay. All right, and so you can see here that because I did that one correctly, then we are Gucci. Okay, so we don't need to flip or anything like that. Okay, any questions on the contact? Okay. All right, and so now that our contacts are good, we can go ahead and apply a mesh. Okay. I don't think we have anything special. Yeah. Okay. So we don't need to do anything special with the mesh, and so the only thing we need to do is make sure the elements are quadratic. Okay. And so I'm just going to go ahead and generate this mesh. Right. So this analysis will work, even with a fairly coarse mesh. So actually the default mesher did a pretty decent job with this. But if you want, you can make this mesh more refined if you like. But for my purposes, I'm just going to leave it as it is. Okay. Okay. And so there's the mesh. And so next we have to add the boundary conditions. Okay. And so the boundary conditions for this and the loading is actually a little bit complex. And so let's spend a bit of time on this. First thing let's do, let's go ahead and fix it. Okay, so let's go ahead and apply a fixed support. And we're going to fix it at the bottom of the base. Okay. And so we have our fixed support there. Right. And so the next thing we're going to add is loads on each of the 4 holes right here. Okay. And it might be easier for you guys, instead of kind of following along with me, it might be easier to look at the document for this, because it's we're basically going to be applying loads on the 4 holes. Okay. And so you can see here that I've applied, I've labeled the holes, A, B, C, and D, and the loads here are given, or the load values are given in this table. Okay. But before you do that, we're going to use something new here that we haven't used before. Some of you have already tried this, I think, in the midterm project. But I think it's useful to kind of go over as a group. Okay. And so we're going to use something called a bearing load. Okay. All right, and so let me go ahead and relabel this. And so this will be bearing load A. Okay. All right. And so we're going to apply the bearing load. So bearing load is a special type of load in Ansys where you can only apply it onto kind of onto a hole like this. Okay. And so there has to be kind of a bearing for it to go into. Okay. And we can apply this, we can apply the loads in terms of components. Okay. And I'm going to go ahead and set the components for the first hole. Okay. And so for this one, which is the hole that's labeled A, okay, I fell into a trap, called it something else in my other lecture, and everyone giggled, so I'm not going to do that here. Okay. And so the X component for this force is 16,000 newtons, and the Y component is 30,000 newtons. Okay. And you'll see that there's a Z component here, but I'm not going to apply the Z component on this one, and I'll tell you why in a second. Okay. And so the question, I think the question, a fair question to ask right now is, what's different about the bearing load compared to like a normal force load. Okay. And the difference can be shown kind of in this figure right here. Okay. And so, let's say that, we applied that same load instead just as a regular force load. Okay. And so we applied like a force boundary condition. So we right click here, we inserted a force, and we clicked on this surface right here. Okay. And we applied the same components, right? And so let's say we put 16,000 and 30,000. Okay. All right, so what's the difference between this force and this bearing load, right? Well, if you apply a force load like this, like a regular, just a regular force, okay, and you apply it on a whole surface like this, what Ansys will assume is that this force is going to be evenly distributed throughout this entire surface, right? And so, you know, we've talked about distributed loading before in this class, right? And so when the force is evenly distributed, it basically assumes that the entire surface is being forced at the same rate, okay? Which for a lot of applications is fine. That's exactly what you want. You want an even distribution of the force. But for bearing loads, you know, we have a unique case where a lot of times bearing loads are there because you have some kind of shaft that's being inserted into this hole and being pulled in a certain direction, right? And so in that case, it doesn't really make sense to distribute the load equally. We want to distribute the load, or we want to bias it towards the parts that make contact with the hole. Yeah.
So if it was a force, if your X component, you did 16,000,
Mhm.
it distributes 16,000 equally, but you also in your Y, you have 30,000.
Yeah.
Will it like screw up ANSYS when we like calculate it?
No, it'll be fine.
Because
Because
it like distribute it if there's two different loads.
it's because in the end you have a total load vector like this, right? And so
Okay,
if you
that's what's good.
right, and so it considers just the single load vector and it distributes that totally evenly throughout this entire surface. Yeah, and so visually, you know, it might look something like this, where you have like arrow, arrow, arrow on all the different aspects of that surface. Yeah. Yeah, but for bearing loads, you know, if you have a shaft that's inside there that's being pulled, you want the force to be distributed only on the parts that make contact with the hole, right? And so you want a distribution that looks more like this, right? And so in this particular case, you know, we have a shaft that's inserted into this hole and being pulled upwards, right? And so since the shaft is being pulled upwards, there shouldn't really be any force on the bottom of the hole because the shaft isn't making contact there. It's only making contact on the top, right? Right? And so in situations like this, where you have a load that's on a bearing, then it makes more sense to use the bearing load because then it'll bias the load, you know, in a better way. Okay? Sometimes it won't make that big a difference. And so if you compare the results with the bearing load versus the regular force, you know, it might be mostly the same. But sometimes it can make kind of a bigger difference. And so, you know, that's the difference between a regular force and a bearing load. Okay. And so for this activity, we're going to apply bearing loads on all 4 holes. Okay. But before I let you go and apply the rest of them, you know, if you notice, I didn't apply the load of 16,000 in the Z direction on this hole, right? And so if you look at the Z direction on this part right here, you can see the Z direction is basically facing axially down the hole, right? And so it's facing into the hole and out of the hole. And so the thing with bearing loads is that you cannot apply any loads that are, you know, in that axial direction. Okay. And so let me show you what happens when you do this. Let me go ahead and suppress this for now. Okay. Let me go ahead and set this to 16,000. Okay. And so if you try to apply a bearing load where you have some kind of component that goes into or out of the hole, and you try to solve it, Ansys will tell you, nah, you can't do that, bro. And so, you know, if you look at this message right here, you know, you read this error message, it says, you have a bearing load that has an axial component. This is not allowed, okay? And so in order to apply that axial load like that, let me go ahead and set that back to 0, okay? And so conveniently, I have this axial, this force component right here. And so you're gonna create a separate load, apply it on the same surface, okay? And you're only gonna apply the axial load here, okay? And so we're going to set this to 16,000. Okay. And so you can see that now we have the axial load applied on this hole. And so the combination of this bearing load and this regular force load together, they form all the load components on this bearing hole A. Okay. All right. So does that make sense about, you know, what bearing loads are and the reason why we can't use axial loads on them?
Good question. So then, did you still do it in component form and running negative 60,000 for the Z?
For hole D, I do that. But for hole A,
For the axial load.
Yeah, for the axial load for hole A, it's a positive 16,000, and so you can just use the the direct values from this table over here. Yeah. And so, it's okay for us to apply multiple loads on the same surface. So remember, I got some questions about that from my grad students. And so it's okay to apply multiple loads on the same surface. That's totally fine. So you can just kind of layer loads on top of this thing. Yeah. Mhm.
So we're saying like the shaft is creating an axial force opposite to where it's connected to.
Yeah. So it basically the shaft is inside and it's being pulled out basically.
Oh,
Yeah. And then the fact that it's being pulled out will create an axial load on that hole. Yeah. Mhm. All right. And so go ahead and apply the rest of the loads onto the holes. Okay. And so you should have 4 bearing loads. Okay. So because all four holes here have a bearing load attached to them. Okay. And so you're going to use a bearing load to apply the X and Y components of these loads. Okay. And you should have 2 axial loads. So one for the hole that's labeled A and the other one for the hole that's labeled B. Okay. All right. And so in total, you should have 6 loads. Okay. And so I'll let you guys kind of do that. Okay. And then I'll come back in a few minutes just to get us to the next part. Okay. And make sure you're labeling your loads just to make it easier for you to see.
So what is the axis? Do we apply the force for the Z component?
Yeah.
Do we apply like it doesn't matter what? I think one of them is negative. Which face do we apply it on?
Yeah. So the diagram for the labels is up in the document right here.
Yeah, I mean like it's like we apply it on the. It doesn't matter. Like I think like there's a circular section.
Yeah.
And we apply it on there.
Oh, so you can apply it on the same surface that you click for the bearing load.
Oh.
And so so you can see for this bearing load right here, I'm applying it on this inner surface right here.
Okay.
And then for the axial load, you apply it on that same surface on the
Okay.
interior. Yeah. Yeah. So you can apply multiple loads on the same surface. That's totally fine. Yeah.
oh.
Yep.
You mentioned we needed 6, so then we still need to add the 0 axial force.
So so for the 0 axial force, you don't need to add anything for that. So you should have 4 bearing loads. So one bearing load for each hole, and then the 2 axial loads. So you have an axial load on the hole A and an axial load on the hole D. And so that's 4 plus 2 is 6 overall.
For the modal part, is it basically like a copy paste of, I mean, obviously modal, but copy like the model and the engineering data from the previous, right?
Oh yeah, actually, we're going to basically link the modal analysis with the static structural, and so it'll import those things all automatically.
Oh, really?
Yeah, so that's why we're kind of spending a lot of time on this right now, because so we don't have to reset it for this for the modal.
Yeah.
Yeah.
Okay, thank you.
And so if you set all the loads correctly, and you can go ahead and run the static structural simulation, you should get a simulation result that looks like this. Okay, it looks a little bit scuffed right now, but it's only because the results are scaled, and so these multiplied all the deformations by 53. Okay, and so if you want to set this to true scale, go to results and then go to true scale. Okay, and then you don't have the flanges popping off of the gearbox. Okay.
Why doesn't it do true scale at the very beginning?
I think because usually the preference that a lot of people have is that they want to see an exaggerated form of the deformation, just so that they can see visually, like, this is how it's going to deform. Because for most fractal cases, it's never going to actually deform this much, but people want to see how it would actually deform.
So in the industry, would you say it's better to do the auto one than do the true?
It depends. I mean, every team kind of has their own preference for it. I would say the auto scale is good for you to kind of see what it looks like visually. But if you're presenting results to like your boss or something, I would not use the auto scale, because if you saw something like this, you might panic and be like, what the hell's going on?
Dr. Chen, what was it again that we could just change the scaling?
Oh, it was under result. And so after you run the simulation and you go to result up here, and then it's this toolbar right here. Yeah. And so the auto scale should be about 53, and then you can change it to true scale. Yeah.
Thanks.
Yeah. If you want to see it really cool, you can go to the 5X auto, and it gets really like kind of crazy like that. It's like a modern art exhibit.
What if it's like the error of actual load?
Wait a second.
Instead of the error for bearing load having an actual component.
Oh, and so if you have that error, then if you go to the bearing, each of your bearing loads, just make sure the Z components are 0. Yeah. So for the Z components, you have to apply a separate load, a separate force load for that. Yeah.
Have them all 0.
Oh, still? Let me see. Yeah. So actually load A and B, these ones have to, these are still there. So you just switch them to like a regular.
Oh.
Yeah. And so if you're finished with this part and you want to get a head start on the activity report, what I'm asking you to do for this part of the problem is to show your total deformation and equivalent stress fields. Okay? So if you want to take your screenshots and put it in like a Google Doc, then then you can get a head start on that. Okay, so is everyone able to get this result here? Good. Okay. So in the interest of time, I am going to go ahead and move forward. Okay. And so all that is just static structures. We haven't really done anything new here. Well, we did do bearing loads, and so that's new. Okay. But now we're going to actually get to the new stuff where we're actually going to solve for the natural frequencies. Okay? All right. And so to do this, we need to add an additional analysis type onto this beyond static structural. Okay. And so I know in the document I told you that you have to close mechanical, but you actually don't even need to do that. And so if you go back to Workbench right here, okay, and the analysis that we're going to do is Modal, and so we're going to click on Modal, and we're going to drag it onto Model right here. Okay. And so by clicking Modal and dragging it onto Model, then this Modal analysis is going to inherit the geometry and the mesh and the boundary conditions for for your Modal analysis. Okay. And so once you've done that, you can go back to mechanical, and just like that, just like magic, you can see here we have another analysis type right here called Modal analysis. Okay. And so I just learned that this mesh actually. I always thought that if you're going to add a new analysis type, you have to close down mechanical and open it again. But you can just leave mechanical open and just click and drag stuff.
Sorry, where did you drag it?
Yeah.
On top of it.
Yeah. So I clicked Modal and I dragged it on top of our static structural like that. And so after you do that, it should automatically link with your old one. Yeah.
And, you're choosing all of the parameters of the initial geometry.
Yep. 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 Okay.
Sorry, I have a question.
Oh yeah, no problem.
Can you do this also with other analysis?
Oh yeah.
Drag the box and then transfer the data.
Absolutely. Yep. And that's how you do what's called multi-physics type of simulations. And so anytime you have kind of more than one thing going on, and so here we have structural and modal, which actually, modal doesn't I don't exactly count modal as another physics type. But let's say that you want to do like a thermostructural simulation. And so you want to serve for both structural and thermal at the same time. You would take, steady state thermal, and then you can drag it on top of here too. And then it'll inherit like the same mesh, the same geometry. So you don't have to do all those things again. Yeah. Question?
Yeah, when I dragged over the modal one over on the static structural, I also have a purple line going from solution setup.
That's fine. And so that's totally fine. And so that's just going to make one small change, and I'll highlight that later. That's actually the better way to do it. But I'm doing it this way first just to kind of highlight the differences. Yeah. Okay. All right. And so let's go ahead and go into here. Okay. And so if you did do that, and so if you drag the modal analysis and you have a connection with the solution, probably what you'll see is that for this setting right here called pre-stress, you might have something here for static structural that's in parentheses. Okay. And so the pre-stress, remember, is a state of stress that the structure can have, and it's going to slightly modify the natural frequencies of your structure. Okay, so most of the time you want to do that, but for now we're going to not include it. And so if you have pre-stress here, go ahead and click on none, and then we'll bring it in a bit later. Okay, and so actually right now the way that we're setting it, the only thing that we're inheriting from our static structural is purely just the geometry, the mesh, and the material properties. Okay, so all the loads actually aren't being applied right now. Okay, and so because we're not inheriting the boundary conditions, we need to apply a fixed support. And so let's go ahead and insert, or you have to right click on modal B5. You're going to go to insert, and you're going to click on fixed support. Okay, and we're going to fix it on the same place that we did before. Okay. And then the next thing we're going to do is nothing. Okay, and so the next thing we're going to do is we're going to click solve. I was getting confused with something I was doing yesterday. Okay, so let's go ahead and click solve. Okay, and so it's going to take a moment. Okay. And hopefully the simulation finishes. Okay. And then once the modal simulation finishes, you can click on solution B6 right here. Okay. And you'll see a table and a chart here appear at the bottom. Okay, so this is actually where we're looking. Okay. All right. And so the most important thing to look at is this table right here for tabular data. Okay. And so what this is showing you is these are the 6 lowest natural frequencies of your structure. Okay. And so the lowest natural frequency is 315.18 hertz. Okay. The next one is 402 hertz, 418, 405, 429, 430, 531. Okay. And so most of the time, we're only really interested in the lowest one because this is the lowest frequency where we're going to have resonance. Okay. And so this tells us what the natural frequencies are. Okay. And so if you're designing this gearbox for, for structural applications, you want to make sure that this 315 is much higher than any kind of, vibrational forcing that this gearbox is going to experience. Okay. All right. And so that's that. And so that's how you find the natural frequencies. You just load it up, you mesh it, and then you hit go. Okay. But there's more that we can do here. Okay. And so another thing that we would like to see is we would like to see the mode shapes, right? And so if you remember from the lecture on Tuesday, right? And so remember we have resonance in our string, right? Then our resonance could take any number of shapes, right? And so we might have a mode that looks like this. We might have a mode that looks like this, okay? Or we had one that looks like this too, okay? Right, and so depending on what frequency that we're loading the string at, we might view different resonance modes, or in other words, different resonance shapes. Okay, and so we can view what those resonance shapes look like for a 3D application like this too. Okay, and so to do that, you're going to click on mode right here. Okay, and so you're going to highlight all 6 rows. You're going to right click on that column, and then you're going to click on this button right here called Create Mode Shape Results. Okay. And then after you click that, and so I'll leave it here just to make sure everyone knows where it is. After you click that, what you'll see is you'll see 6 new deformation fields appear under solution B6. Okay. Right. And so you can see here that I've clicked on that, and so now I've created those six solutions. Okay. And so you're gonna need to hit solve one more time. Okay. And so what these 6 deformation fields represent is they represent the resonance shape for each of those frequencies. Okay, and so total deformation 1 right here represents the resonance for 315.18 hertz. Okay, total deformation 2 represents the resonance for 402. Okay, total deformation 3 represents the resonance for 418, and so on and so forth. Okay, and so from this you can see basically how your structure is going to deform when it's resonating. Okay. And if you want to actually see it, see what it looks like, okay, you can click on the play button. Okay. And so you can see here that the structure is kind of vibrating kind of left to right. Okay. And so what does this mean? And so what this means is that if you remember that this is a gearbox, right? And so we have a bunch of mechanical gears on the inside. If the gears are rotating at a particular angular velocity that is equal to 315.18 hertz, okay, or around there, then your gearbox is going to start to vibrate like this, okay? And so it's going to basically kind of sway kind of back and forth with this part here kind of bulging out, okay? Right? And so this obviously is not good, okay? And so you want to make sure that you avoid cases like this, okay? And then you can view the resonance for each of the different modes as well. And so if you end up at 402 hertz, then the resonance will look something like this. Okay.
Dr. Trans.
Yep.
I think I'm getting different tabular data.
So do you have the pre-stress here for is it static structural?
It's none.
Oh, it's none. Okay.
I got For my first one, it's 318 something, and they're just quite a bit higher than, all of them are quite a bit higher than what you got
Okay.
here.
Did you change all the material properties here?
Yes, I did.
Okay, let me take a look after
Okay.
this. Yeah,
Oh, let me just double check.
question?
So the frequencies that were given are basically saying that at these frequencies resonance will be hit.
Exactly. Yep.
When we did our initial data for like materials.
Yep.
We just used materials in the library already.
Yep.
Was there any specific things that was included that we need to know about?
Yeah, that's a good question.
Okay.
Yeah, so if you're adding your own material data here, the most important things you need are the density. Let me look at stainless steel actually. So you need the density and you need the Young's modulus. The Young's modulus and the Poisson ratio.
Okay,
And so
same as usual.
Same as usual.
Okay.
Yeah. Except I think we didn't add density before, but you need to make sure you add the density. Yeah. Mhm. Yeah. So this isotropic coefficient of thermal expansion, that's for thermal. You don't really need that, but yeah, the only things you really need are just the Young's modulus, Poisson's ratio, and density. Yeah. Okay. And so this is what's called the unstressed natural frequencies, right? And so this is without any of the loads that we applied before. And so now let's look at the case where we actually apply our static loads from static structural and see how that changes our natural frequencies. Okay. And so under pre-stress here, and so here you're going to click on static structural. Okay. All right. And so after you click on static structural, you can see that our fixed support here is now a question mark. And the reason for that is because we have kind of a redundant fixed support, because now it's inheriting the fixed support from static structural. And so we no longer need this. And so we can right click this and click suppress. Okay. And so unfortunately, this is not going to work for me because this computer is bugged. But if you run this modal analysis again, what you'll see is that the natural frequencies should increase a little bit as a result of the pre-stress. Yeah. Good question. So there's a question in the chat. So how do we determine how many modes we need? And so if you go to analysis settings, this was the thing I was looking at before. And so the default here is to solve for 6 different modes. Okay. Most of the time, you're not going to be interested in anything more higher than 3 or 4 or 5, because usually a resonance is kind of approached from below. And so what I mean by that is like let's say that you start rotating gears inside this, and so the gears are going to speed up from 0 and go up to like a higher frequency from there. And usually once you hit resonance at one frequency, then that's usually something you want to avoid anyway. So actually for most cases you're only really interested in just the lowest natural frequency, which is the fundamental frequency. But the other ones are included just for kind of interest's sake. Yeah. And so six is fine, but most of the time you're only interested in just the first few. Yeah.
So going back to the kind of like so if we're designing something, we always want to design the frequency of whatever we're designing to be much greater than fundamental.
And so there's 2 things. And so there's the frequency of the forcing. And so whatever vibrating component that you have in your structure. And so for this case, since we have gears, it would be like the RPM of the whatever gears that are inside. You want that forcing frequency to be usually much less than your fundamental frequency. Yeah. Because when that happens, then no matter how fast your gears are spinning, even when it reaches its max speed, there's no way that you can achieve resonance inside your structure. And remember, resonance is something you always want to avoid. Yeah.
So instead of having it much higher or much lower, or does it make a difference?
And so you definitely want the forcing frequency to be much lower than your fundamental frequency. And so for this particular case, let me switch this off again, just so you can see. And so for this particular case, where the fundamental frequency was 315 hertz, I would only feel good about the structure if the forcing frequency was like 150 hertz. That means like the maximum gear speed is not even going to get close to resonance. Yeah.
And then question.
Yep. Mhm.
So is the frequencies work the same way where in order for it to be more accurate, we need to purchase the mesh?
Yes, yes, yeah, definitely. So if you yeah, that's definitely something that you should do. So if it's definitely good to check the convergence of modal. I actually don't know how quickly modal converges. My impression is that it actually converges very quickly, and so I don't think you need that refined of a mesh to get an accurate modal analysis. But I could be wrong on that because I've never actually tried it myself. But my impression is that it's not that sensitive to the mesh.
Sorry, last question.
Mhm.
And is there any reason why, at least for me specifically, my fundamental decreased instead of increased? So it's that expression.
It should increase. I think maybe I'll come by and take a look. Yeah. Was everyone were other people able to run it with the pre-stress, and did you see the fundamental decrease or increase?
Mine decrease.
Oh, decrease. Okay.
Decreased.
Maybe I'm getting it mixed up in my head. Maybe it should decrease.
Mine increase, but like it doesn't differ either. It's like non or static structural. It
Okay.
just gives me the same result.
Okay. It shouldn't make that big a difference, and so it should only be a very minor thing. Yeah.
I guess also on the side note, I got an error for because we assigned the static structural resource. I got a large deflection error.
Oh yeah. So Preston was getting the same thing. So if you want, you can go ahead and turn on large deflection to get rid of that message. And so if you go to analysis settings here, you can go turn on large deflections. And so these are the analysis settings for static structural. And yeah, so you can go ahead and do that. And then that'll change your results a little bit. Okay. Okay. And then let me see actually if this is actually going to work. Let me try. Nope. Okay. So this is the same error as I did before. Yeah, actually, I don't remember. Yeah, if your fundamental frequency decreases with the pre-stress, and that's fine too. Yeah. Maybe I think I'm remembering it backwards. Maybe it should decrease maybe with the pre-stress. Yeah. Okay. And let me actually turn this off. And so I'm gonna let you guys go in a second, but I do want to talk about one other thing before I let you work on the rest of the activity. Okay. All right. And so these mode shapes, okay. And so so the mode shapes that you get from viewing from the different mode shapes, it's really these results are really misleading, because if you look at the color bar here, okay, it'll tell you that the deformations here are like 12.781 millimeters, okay? And so, I want to caution you guys to not take these results seriously, okay? And so what I mean by that is that these are not the true magnitudes of the deformation, okay? And so the only reason that these graphs are colored the way they are is just to illustrate the shape of the resonance to you, okay? But the actual values of the deformation, they hold no meaning at all, okay? And the reason for that is because we haven't actually applied any kind of loading to this yet, okay? And so we don't actually have any gears that are rotating on the inside that are applying any vibrations. And so there's no way for this number to actually be physical, okay? And so be careful when you're viewing the mode shapes. And so when you're viewing these mode shape results, these are only here to just show you what the shape looks like, but they don't actually, the actual values of the deformation don't have any meaning at all, okay? And so just be careful with that, okay? And so for this class, we're not going to do anything with that, but if you end up using this for one of your projects, or if you go out in industry, don't take these mode shape results at their word, okay? And so to actually view the true deformation, or to do a true vibration analysis, we have to do what's called a harmonic response analysis, which is, which is here, which unfortunately we don't have time for in the class, but that option is available for you. Okay. Okay. And so with that, that'll get you through problem 2 on the homework. Okay. And so, make sure to grab your screenshots before you move on. Okay. And so problems 3, 4, and 5, I basically want you to kind of play around with some of the settings and see how that affects your results. Okay. And so for problem 3, I want you to change the material properties. Okay. And so you're going to repeat basically problem 2, but you're going to do it with 2 different materials. And so you're going to choose one material that's stiffer and another material that's less stiff or more flexible. Okay. And you're going to show how the change in material affects the natural frequencies. Okay. Problem 4, you're going to change the geometry. Okay. And so you can change any aspect of the geometry and then see how that affects your results. Okay. And so this is a design modeler geometry, and so you can actually model it. You can actually modify it in design modeler here. Okay. Or if you want a cheat code that I didn't tell my grad students, another way that you can modify the geometry is you can simply just change the thickness of the housing. Okay. And so you can change it to be thicker or lower, or thicker or less thick. Okay. Thicker or thinner. And then that'll count as a change in the geometry. Okay. And so go ahead and change for problem 4, change the geometry and then see how that affects your results. Okay. And then for problem 5, I want you to actually do some vibration design. Okay. And so, just like we've been talking about, the reason you do modal analysis is you want to make sure that your structure doesn't have a fundamental frequency that's, that matches your loading. Okay. And so for this problem, I actually want you to do something unique for this problem. And so instead of going higher with the natural frequency, I actually want you to make it lower. Okay. And so based on what you learned from problems 3 and 4, apply some of those changes so that your natural frequency is in the range of 190 to 210 hertz. Okay. And so as long as you're within that ballpark, then that's fine. Okay. And then once you've hit that target, then describe the changes that you made and show the six mode shapes. Okay. And then problem 6, as usual, is just to summarize your results. Okay. Okay. And so that's the activity. And so I'll walk around a bit just to kind of help people that are still kind of struggling a little bit. And if you have questions on the Zoom call, just drop it in the chat and I'll come around to that as well. Okay. But we have about 15 minutes left in class, and so you're free to keep working on this. Or if you want to go, then that's fine too. Okay. All right. So I'll start making my rounds right now. We're able to.
Yes. This is what's happening.
Okay.
This is like 318.
I see. So all the materials and everything is
None.
okay.
With
None.
a fixed support.
Fixed support.
If you change it to add structure and suppress this one.
No. It is like a super. Yeah.
You can just hit the chat. So go ahead and click on.
It's the same thing.
So the same thing.
It just doesn't make any difference.
Okay.
If you use non.
I wonder if it's a calculation error. Because so these computers are actually they're all old. These are all grandpa computers actually, and so they're actually slated to be replaced over Christmas break. And I know actually that in this first row in particular, there are a few computers here that have been having issues, at least for my other grad students. So it could just be something like that. But that's okay. I mean, you can just report the results as it is. That's
And I can just, I think I can change it like, you mean like if I do it in a computer, it just, the solution would be like.
yes. So if you do it on another computer, even maybe this one, I don't remember. One of these 3 computers
I think
just
it's
doesn't.
still sign in the back to make sure. that
Yeah,
it's
so I think the ones in the back definitely work better. But for the activity, I mean, the point of these activities is just to kind of teach you these features. And so and I grade the activities on completion. So this is totally fine. So you can just report that. But if you're curious to know, you can either try it on the virtual machine, or you can try it on your phone laptop and see if you get something different.
The virtual machine is just basically connecting to these computers, right? Or just.
It's an instance of these computers, but it's not exactly.
Okay. Thanks.
Yeah.
So then the this year it's good fundamental.
That's usually the one.
It's stuck. So this natural. So this is.
Yes.
And so then usually we would want to be designing something we want the resonance to be much lower than natural.
So the resonance frequency, I think, that's the frequency where. So the two frequencies you should be controlling are the frequency of what's called, what I call. So usually you have some sort of experimental test here that's going to revise the characteristics of that one. In this case, it could be your or it could be like that's another one.
It's a triangle.
And so that frequency of whatever.
So I guess T
should be much lower.
triangle.
Should be much lower.
And it's supposed to be. It's supposed to be so variable. So it's like the frequency is like something times 10 to the negative.
So that
Here, my answer was times 10 to the 4. So this sounds like but we never really tried to do sphere or circle.
Spears and.
So all these little
These are not my questions.
Yeah.
So I wanted to just ask them.
So this frequency right here is the natural frequency of the entire universe. So I think another easy example to think of it is like an earthquake. So you're designing a building and you see that the natural frequency of the building is like 290. And so if you look at the frequency of the earth, so your earthquake's going to flash. So the earthquake frequency is much lower than whatever you're doing.
Okay.
Because when things start vibrating, you're always focused on the flags started with low, they can start vibrating. And so whatever like let's say whatever that frequency, it should be much lower than whatever standard frequency.
So that, so they try to, if there's no way around, kind of like the measures, so there's no way around to vary the mode of line. So then we would have to actually change the geometry to force the natural frequency.
And most of the time you don't have control over it. And so yeah, you're using that.
Yeah, just another question. So I think scratching yes, that is stretching. And I also defined mesh through.
Okay.
And it lowered my stress. And then, my frequency.
Yeah, that's fine. That's because once you turn on arc deflection, you're considering non-linear effects as well. And so that's going to change the results. Okay. Yeah.
You showed me what they say in properties appropriately.
Yeah. Yeah. So you go from workbench, you're going to go to file.
Yeah, file.
And then
Save as.
archive.
Okay. Oh,
So if you save as, it's going to save multiple files, but for archive, it's going to save like a single zip. Yeah. And then once you open it up later, then you just unzip the file. Basically.
and that's pretty much it.
Yes.
All right,
So-
I was gonna transfer it over to.
Oh, first I have to save the project. So this is the file that you want to transport. So this is an archive file, the WBPT.
Okay.
And so that's the file that you either move to your flash or you build yourself. And then once you're on your other computer, you just double click that file.
Oh, I see. Okay, I'm gonna put this on the desktop.
Yeah.
Cool.
Yep, and then you can just say it.
Cool. All right. Awesome. Thank you.
Mhm.
Do you think it's possible if I could change the topic of my phone?
send me an email, just let me know what you're doing. If you have a CAD model and you have a screenshot of that, then just describe it. So you don't have to write a whole proposal, but yeah, just let me know. Yeah.
When you get a chance to make like that.
Okay, yeah, let me
Yeah. I'll send you my updated CAD file, because I like mine.
I started off with like this.
See you later.
Jesus Christ,
I slept in my last one.
So that's your
So I read the simulation, how it was before, and I didn't, like, nothing really happened.
because you need to fix it. So since we're not in very
I'm gonna email this to myself as well, because I feel like.
So when I did it before, I felt this at first, and it kind of looked all the same, is that just because?
Oh, did you run it?
Uh-huh.
Oh, okay. Go ahead, run it. I forget this.
I had the little, like, table down here with all the notes.
So
But then I clicked it, and I think I did copy the data or something like
Oh,
that,
okay.
and it shot.
I heard you say that,
Over
I
there
don't really
with the
believe
face.
it. I mean, there's
I see.
there's probably no chance.
Yeah, once that finishes.
So that's what I'm saying, but there's no way.
Yeah, it
these
took a while.
It's gonna happen. Oh, I know. When it's paid and it was paid,
Well, this is
it was-
Yeah, so when that finishes, and hopefully we'll have we'll have the six.
Not only the
lowest one should be the ball.
Yeah, I know, or yeah, the lowest one's 3.
Okay, okay, yeah, let's go. Okay.
But that was, I guess, like.
I'm not following that.
Okay, yeah, the pre-stress, for some people, it seems like the pre-stress is a very. Because when I did in my office, I got the same results.
And it does seem it's just across these.
Did you upload it?
Yeah. It's close.
Yeah, there you go.
And I also.
Okay, yeah, don't worry.
It just very.
Okay. Most projects shouldn't take all that. So.
I used to do that when I had chats, like, in projects, and so I always like, I always. Other people would go to. They might know it, and then we just do their stuff, and it's just.
I think probably the only way to probably fix this is. Just make sure you say
You got rejected.
Yeah, I think there's some weird crap.
That's really rejected.
I know.
It pops up like a full mailbox.
I think I should have answered there.
I see. Yeah, I can have it. So, yeah, the old reset the program, that's the cure all.
Yeah. Work in this case. Thank you.
Yeah. How are you guys doing, Zoom people?
I'm good.
Good. Okay, I'm gonna go make another round. So we have 5 more minutes left in class, and so in case I don't make it back here by 6:45, thank you guys again for for coming today. It's the last Ansys activity. Next week we're gonna just do miscellaneous stuff, and I've just realized now I didn't put out the poll, and I'm a lot of things are kind of slipping this week, and so when I get back up to my office, I'm going to put out a poll so you guys can vote on the topics that you want to see next week. Okay, and so all the topics I have already, and so they're basic all of the appendix stuff that you see in the lecture notes section of the class website. And so if you go to files here and you go to lecture notes, all of the lecture notes that have an A next to them, are fair game for next week. And so, just take a look at the titles here and just see which ones that you want to learn about. And then I'll cover them next week. Okay. All right. So if I don't make it back to the lecture before 6:45, thank you guys for coming again. Hope you guys have a good weekend, and I'll see you guys next week.
Oh, yeah. Professor, did you do the exams by chance?
Yes, they're in my office.
Yes.
Okay. I'll get it after this.
All right, for sure.
So Madison, the
Uh,
what do I need to do to add all the other stuff?
Yeah. So click on.
Honestly, yeah.
Honestly, I'll find out.
You should open it and check.
You
You gotta wait for 5 minutes. till you
might have hit solve over time. I mean, right off my office. I take exams.
Yeah, boy.
I completely forgot about the.
That's why you came here,
Yeah, that's exactly what. Thanks for reminding me. I drew them like 2 years ago.
Right. because of the recap.
It's like I eat something like this. and-
Could you get this part off for me? I need to read it, so.
What?
Yeah, bottom up top. About a few hours. man. You know?
There's- and then, yeah, it's that, some- yeah, it's extremely tricky. But, I don't know what it's really, I mean, obviously it's like some kind of rubber plastic, but they lost your
Maybe I just like that.
Uh,
I don't know, because I didn't like see any of the years.
For
but,
reason
yeah.
scientific term.
Yeah, creepy for more or less, I think like. Or it's actually a concept.
Yeah.
Is what I had.
Yeah, exactly. right. I mean, it seems like they just were pouring like their predictor. And it's fine, but we decided.
I like how you
I don't know,
ignore view with the picture. Yeah.
It's like there's one of those.
Just true.
Maybe. Are you being calculated?
All right, I'll take exams.
Even though I know I did already.
Oh, it's good to take it home and see. All right, you gotta go ahead. You're just ended up.
Thank you.
From Brandon, let's see how Brandon did. Oof, Brandon, 10 out of 40.
Dr. Tran,
Yep, what's up?
the deformation fields, you wanted pictures of the stress-free with no pre-stress,
Yes,
and then you wanted the static structural pre-stress.
yes. Yeah.
Okay.
Only for problem 2. So for problems 3 and 4 and 5, you can do it without pre-stress.
Oh, okay.
Pre-stress is only for
Without.
problem 2. So 3, 4, and 5, no pre-stress at all.
I got you. But every time we do it, we have to make sure that we suppress the fixed support for the modal, correct?
Yes, yes. Mhm.
Out of 10. 9 out of 10. I wish that the teacher hates me or something. You know? That's what it is.
I'm pretty sure, yeah. He has good reason to.
Oh, yeah.
For final presentations for the analysis portion, we have to also show like some reasonable arbitrary numbers for like.
Yeah. So
Same
someone
as
asked,
a result, right?
yeah. So someone asked me about that today. So if you can't find like reasonable weights for like the different body parts, you can just use some of the examples that we did in the class.
Okay, most likely this should be enough.
Yeah. So it seems like some groups are having trouble looking those up online. And so if you can search it up online, that would be, I think, the best thing. But if you can't find it, then just use, I mean, all the ones in my, in the lecture notes would be for pretty average people, so that should work. pretty well.
All right, cool, cool.
Yeah.
Yes, let's see what's up with that task.
Yeah, I'll ask. Supervisor.
Yeah.
in order.
Okay. All right, Zoom people, any final questions before I close it up? Okay, all right, so I'm gonna close up the Zoom call, so thank you guys for coming today. Oh, Steven, do you have a question?
No, I was just saying thanks.
Okay, yeah, no problem. All right, so I'll see you guys next week.
This one has like 10. I just wrote